Okay. So today I'll be talking about connecting automated speech recognition to transcription practices. This is a collaborative work with myself, Bradley McDonald, and then two of our collaborators in Indonesia, Johan Safri and Wawan Saharosi, who have been part of this project for many, many years now. So to give some background before diving into automated speech recognition, Nasal is a language of Western Indonesia. It's an Austronesian language. It's spoken by about 3,000 people in southwestern Sumatra. By the Language Endangerment Index, it is considered endangered. So it has 3,000 speakers. It's not used in official capacities. Intergenerational transmission isn't continuing as much anymore. And the language wasn't known to linguists until a regional language report in 2007. So there's very little previous work that has been done in documenting or creating resources in the language. And sustained intensive contact with neighboring Malaic and Lampungic languages have greatly affected the language. And as we'll talk about in a little bit, this is also part of the challenge with working with this data is that a lot of it is multilingual. Okay, so the documentation project from which this work came out of began in 2017. Like I said previously, there is little prior existing documentation. So there are 3 written sources, but no audio or video recordings with transcriptions to work off for developing an ASR model beyond what was created as part of this larger project. So since the beginning of the documentation project, a relatively large corpus of conversation, elicitation, and narratives has been produced. This is primarily conversation. That is the large bulk of the corpus, just everyday conversation, people talking about their daily lives. This is approximately 360 hours total in recording time. And of this corpus, about 50 hours have been transcribed. Again, most of what's been transcribed has been conversations. So not a lot of narratives. There's not much of a local tradition of telling narratives about local history or songs or anything for that matter. So it's most of it is conversational data. So whenever we're talking about working on transcriptions in with Nasal, there are 4 primary steps in the workflow. The first is to segment the speech into we work with intonation units, so just how speech is naturally broken up according to your prosody, and then transcribing those segments, and then adding additional notes for discourse. So this is things like breathings or glottalizations or different false starts, different things that are marked in speech, and then adding translations for Indonesian and English as well. And then the last step is to add additional context. So if there's a pronoun, who does the pronoun refer to? If there's a specific name, who does that name refer to? And so that would take place in the 4th step of the transcription. And given that the time to transcribe audio is often upwards of 40 times its length, we can see that the 2nd step is going to be the most time-consuming step in the process, and that's what we aim to address with ASR. So our motivations for working with automated speech recognition for this project in particular is, well, first of all, we have sufficient input. There's a relatively large corpus of transcriptions that have been created by Johan Safri and Wahan Saharosi as part of this project. And we have a large corpus of untranscribed recordings that can be used for testing. And then there's also, in recent years, a much more wide availability of pre-trained models that can be used for fine-tuning ASR to work with under-resourced languages. And this would also be very valuable for the output that it produces, right? So the manual transcription process, normally about every month, Johan and Wawan can transcribe maybe 30 minutes of speech. And so with that slow progression, the ASR can hopefully, we aim to find out with this project, speed up that process because all the linguistic analysis and the work that we're currently doing on developing a Nasal dictionary rely heavily on the transcriptions produced from these recordings. So with those motivations in mind, the main goals of this project were to assess the feasibility of implementing ASR in a typical documentary context, to determine if the results that were produced from the output of that ASR model are adequate, and then knowing the limitations from the ASR model and from the data that we have available, determine if ASR could even help speed up the transcription workflow. Okay, so now actually diving into the automated speech recognition system. So the data used for the model development, we took transcriptions of 25 of our recordings. This included primarily everyday conversations, because like we said, this is the majority of the speech in the corpus. 10 recordings of prosody elicitation. These are actually much shorter than the everyday conversations. So the everyday conversations can be between about 1 and 2 hours, and the prosody elicitation is normally about 30 minutes. And then 2 semantic domain elicitation sessions. And this is, discussing words for a specific semantic domain for the dictionary development. And these last normally about 3 to 4 hours. This data included 49 data from 49 unique speakers. 7 of them were represented twice in the data, and 1 of them was represented 3 times in the data. And this diversity in both speakers and genres reflects the intended use case of the ASR model. So aiming at producing transcripts for all of the data that we have in the corpus for primarily the dictionary development at this time. So from this data, it was all 25, so it was 25 recordings, and it actually wound up to be 25 hours of recording time. And based off of the time codes from the transcripts that were produced in ALON, we were able to clip the speech segments from those individual speaker audio files from the recordings. And after clipping all of the data, removing all of the empty speech, all the silence, there was 17.5 hours of actual speech, about 160,000 words, and 66,500 annotations. And then we split this data 80-20 for training and testing data for running the ASR model. So the model itself was run by fine-tuning Whisper's small ASR model because of the resources that we had available to fine-tune it. It was utilized the pre-trained tokenizer and feature extractor from Indonesian. So starting off from a related language and then using that for Nasal. And then it was run over 5,000 steps with evaluation of word error rate at every 500 step checkpoint. So we had 10 different points at which the ASR model was evaluated. And then the best checkpoint was used in generating test transcriptions. So the results from the ASR model, we can see the 10 output of the output of the 10 tests here. The final checkpoint was the one that produced the best output. It was 43.9% word error rate. Sounds high, but this is a significant improvement over our previous model from 2 years ago of a 67.2% word error rate. We tested we used the checkpoint that was produced from this final run, and we ran it on 2 segments that were not included in the model development, and they produced a 60% and 54% word error rate respectively for everyday conversation and a dictionary recording, and then about 20% character error rate for each of those. And these word error rates and character error rates actually correspond exactly as we would expect with the distribution of word length in Nasal. So we heard earlier on ASR models with polyfunctional languages or polysynthetic languages with much longer word lengths. Nasal has on average 4 or 5 character words. So this is exactly what we would expect for the correspondence between character error rate and word error rate for a language with word distribution like Nasal does. And then after running the ASR model, we worked with our collaborators in Nasal at just doing a short transcription task to see if correcting the ASR generated transcripts would even be useful at helping speed up the transcription workflow. So in order to do that, we compared manual versus ASR assisted transcription. We selected 4 2.5-minute segments, so 2 of each from everyday conversation and 2 from dictionary recordings, and then 2 that had empty annotations, so the annotations had already been segmented out, but there was nothing inside them, and then 2 where the segmentation had already been done, but they were filled with the ASR generated annotations. And this is work that they've been doing for a long time, so it's very familiar for them to work whether from the blank annotations or from the ASR generated transcripts. And then we did a block design for transcription. So each of them started off with an automated an ASR generated transcript for one file, and then the other for the other file, and then they went to the empty transcript, and then they did the reverse for the second file that they each worked on. So it was balanced for which file they saw first. And then this is intended just generally as an impressionistic evaluation of the ASR's effectiveness. Since they've been working with the transcripts for a long time, we wanted to see would implementing something like this actually be useful to them in their transcription work. And the results of this task, we screen recorded the transcription process of the 4 2.5-minute segments, and comparing the times of the transcription recordings, all 4 times showed faster transcription times for correcting the ASR transcripts than from working from scratch, from anywhere from 11% to 30% improvement in transcription time. And this is the greater improvement was as expected whenever the ASR generated transcript was corrected second, because they had already been exposed to the file one time before that, but still anywhere from 11 to 30% in that range. And then most often the changes that were made during the transcription were single letter or single word edits that really got the entire annotation completely wrong. And from their working with the empty annotations and the ASR generated transcripts, they saw that the revising the automated transcription was actually, they preferred it much more than working over transcribing from scratch, because they had something to work off of rather than having to generate themselves, and that the audio needed to be listened to fewer times in order for the speech to be accurately determined. So rather than listening to an audio clip 10 times, they might have only had to listen to it 5 times in order to determine, okay, this is the proper annotation for this segment. Okay, so with all of that in mind, first thoughts on the model, 43.9% word error rate does not seem very strong. However, the typical documentary data has shown that it's sufficient for developing an ASR model with usable word error rate and character error rate. So by typical documentary data, we mean conversations. So messy data, speaker overlap. Very little of this was very clean data. So single speaker audio files or narratives or very continuous speech. A lot of this was broken data in certain regards. But using the ASR generated transcript actually proved very effective in both impressionistically on how they, felt the transcription process went, and in terms of how much time it took. And then also we see that the time, cost, and software were not prohibitive for using the ASR. I'll talk about the time, the cost at the end, but the time for developing this ASR model and actually running it was not a significant amount of time, especially for being able to implement it in a documentary context. So if that's the case, then what is holding it back? Why the 44% word error rate, and what are the next steps for this model? So I have a lot of limitations listed here on this slide that might have been causing the the high word error rate. So some is spelling variation. There's not a standardized orthography in Nasal. So writing diphthongs in the middle of a word introduces different variants for the word spelling. Different shortenings. So a word like Janu might be shortened in speech as nu, with the first j not even pronounced, but it would still be spelled out in writing. And then discourse marking. So a lot of the transcription, even in the baseline tier, includes things like and and in the transcription as markers for yes or things that you would see in discourse, and these might have thrown off because they're not very consistently transcribed. So at one point you might have with one M, or you might have it with 2 M's, and the same for the others. And then this data also, the individual speakers were all wearing individual mics, but despite that, there's a lot of signal bleeding between the different speakers throughout the recordings, and the audio clarity is very questionable at times, with chickens crowing in the background, or downpours, or children running in playing games. So it can be difficult to understand the speech. And then in terms of the model limitations, we started with the Whisper Small model. We actually went up running with the medium model later too. But the small model, we think limited the word error rate on this. And then the availability of computational resources, and then the limited training time that we gave it. So we only did a 1-day training at a time. So future prospects and how we can further develop this ASR model. We would love to do a further study on the viability of utilizing ASR to assist in transcription. Like I said previously on the transcription task, very impressionistic. And testing with 4 2.5-minute segments doesn't exactly prove that this is 100% going to improve transcription time overall. So we would like to be able to do a further study on the viability of using ASR, and then additional development of the ASR model. So increasing its size from the Whisper size that we used, normalizing the transcripts, and adding additional training data would hopefully be able to help make the ASR model better. And then determining the point of diminished gains in training. So if we go, I'll go back really quickly. We can see here that in the last few runs of the ASR model, there was much diminished gains on how much the model actually improved. So we'd like to be able to see at what point does that really stop improving the model. And from the earlier ASR talk, possibly attempt adding additional artificial data to assist in the ASR model's development. I also have a note here at the bottom. This isn't what we use to run the transcription task, but after running the transcription task, we decided to add in some more data, run on the Whisper's medium model and partially standardize the spelling to see if that could improve the word error rate, and it did. So going from 44% to 37% word error rate, and from 20% character error rate to 14%. So in response to the goals that I mentioned at the beginning of the presentation, for time, cost, and data, ASR is feasible for the documented context. The cost for this was covered by Google research credits, which it seems like they're pretty generous with. So that's available for using for getting computational resources to fine-tune such a model. And then the 37% and 14.4% character error rate adequate for using an ASR model in the documented context? We think so, especially because Johanna Wellman appeared to definitely said that they favored working with those transcripts than working from scratch, and it significantly helped speed up the transcription process. And we would love to hear any suggestions, feedback, or interest in collaboration on this project in the future. So thank you.
Well, it's nice to see. I was curious when you're talking about, needing sort of more evidence. So there's been a few of these papers now, right? Do you think that it's safe to say at this point that this is going to work for arbitrary language? Or do we need to worry about generalization in new contexts still?
It would seem to see from, like you said, there have been a few papers out already on this and from a very wide array of language families, and all of them seem to be in the affirmative that using ASR in the documented context is going to help speed up transcription, and that transcribers, and it's not very much discussed, but that transcribers do prefer working off of this rather than empty annotations. And what we're seeing here, it seems to be the case as well. Now, do the models need to be improved? Absolutely. But I think it's at least a starting point to be able to work better off than working from scratch.
I have a question. So you have trained that it's late. May I know that